Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Guwahati University of Science and Technology. I welcome you to the course PHY 352 Nuclear Physics 1. Today I will be covering the ninth lecture of this course, and the topic is nuclear binding energy. First, I will give the learning objectives uh, that at the end of this presentation, the student will know what is meant by nuclear binding energy, and that arises because of the mass defect. Now, they will be able to understand the neutron and proton separation energy, and also they will be able to understand the trend that the nuclear binding energies of the known elements. By known elements, that are the elements of the periodic table, and some of the elements, mm, mm, those are made in the laboratory, the stable elements, how their binding energies varies with the mass number A. In this course, we are following the book Introductory Nuclear Physics by Kenneth S. Crane, 3rd edition. Uh, in this presentation, some of the illustrations are taken from this book. Now, since we know that the nuclei are composed of protons and neutrons, that we have discussed in the first part of this course, that these nucleons are localized inside an atom to a very small regime, such that the radius of the nuclei are in the femtometer regime. Now, to understand the binding energy, or the energy at which these nucleons are bound to each other, we need to start with the fact that the mass of a nucleus is always less than the sum of the individual masses of the protons and neutrons which constitute that nucleus. To understand that, need to use this cartoon here. Now, by this statement, if you want to explain with this figure, in this nucleus we are having 3 protons and 4 neutrons. Now, the fact is that the mass of this nucleus is somehow lesser than the mass of 4 neutron and 3 proton. That is, there exists a difference of mass, and that mass is actually appears as binding energy. That is, this much energy is required to separate these nucleons. Now, those nucleons will be having greater mass than that system. So, one can say that that difference of the mass, that is the missing mass, is the measure of the nuclear binding energy which holds the nucleus together, or we can say the nuclei together. So, the question is that some mass is missing, and that appears as an energy. So, the next thing that we need to think, how to calculate the nuclear binding energy that arises from the missing mass, or the missing mass give rise to the binding energy. Now, to answer this, Einstein determined that matter could be thought as a form of energy, such that there would be a quantity called the rest energy, which would be the amount of energy that composed a piece of matter. And his famous equation, the rest mass energy is given by E is equal to mc square. Now, this Einstein's equation not only says that mass and energy are equivalent to each other with the speed of light as a conversion factor, Or in another word, we can say that, or one can say that this energy uh, and mass are just the same thing. That is, mass is a form of energy and they can be interconvertible. So, how one can use this expression to find out the binding energy that we have discussed on the previous slide? That is, some mass is missing if we measure the masses on the mass of the system, and also the mass is the combined mass of the individual nucleons. So that missing mass is actually the energy. So how one can use this expression? So the nuclear binding energy, which is just the same E, but in nuclear physics, instead of this E, we have B for the binding energy. And how much mass is converted into energy? So that is that the difference of the two masses. So we need to find out the difference of the masses between this nucleus, the system, and also the individual uh, constituent nucleons. So if we find out their difference, then one can multiply it with c square. So that will give us the this binding energy for that particular system. So we'll be using this thing for the nuclear binding energy. Now to understand this concept with the help of the Einstein equation, we need to start with this binding energy, which is just the same, that it's like similar to E is equal to, this is the m and then c square, but instead of m we have some mass, that is the difference of these masses is converted to energy. So we need to find out that mass. So this mass is somehow greater than this mass, so we need to subtract the mass of the proton and neutron minus the mass of this nucleus. Z represent the proton number multiplied by the mass of a single proton, plus n represent the mass of the number of the neutron multiplied by mass of a single neutron, minus this mn represent the mass of this nucleus multiplied by c square will give us the binding energy. Now we need to simplify this equation. That is, we need to first write this mass of the nucleus multiplied by c square in terms of the atomic mass, since atomic masses are well tabulated because they are easily they can be easily measured instead of the nuclear masses. So we need to convert this mn, which is the nuclear mass, times the c, that is the nucleus rest mass energy, in terms of the atomic masses. So in atom we have the electron, so this is just the same concept for the atoms. Since the electron binding energies are small compared to the rest mass energies for a nuclei, because these are in electron volt or in kilo electron volt, but this rest mass energy for a nuclei is in mega electron volt. So in comparison to the magnitude of this mnc square, one can neglect this part, so that this above equation can be expressed in this form now, where this b is the same, this z times the proton mass plus n times the neutron mass, and then minus, and instead of this mnc square one can write this mac square and also minus the electron contribution. Now we have bring this x for any arbitrary element, right? So in the periodic table, for example, if we pick any element, and that will be having a, that will be having mass, that will be having the proton number and the neutron number, and from that data one can find out the binding energy for that particular system. Now another thing is that one can combine this z times the mass of the electron and z times the mass of the proton in terms of the hydrogen atom. So if we take this z common, and then m plus e, that will be converted to like a z neutron, a neutral hydrogen atom. So again, this is an uh, uh, atomic form. So this is the expression that one can use for the binding energy of any element in this thing. This is just a random x. Now to work with this expression, one need to have some useful conversion. The first one is very simple one, that we know 1 electron volt is this much joules. Since as I told you, the nuclear mass energies are in mega electron volts, so 1 mega electron volt is this much joules. This is a handy one. And then we know that in the periodic table or usually elsewhere, you have these masses given in atomic mass unit. So how one can convert the 1 atomic mass unit to in terms of kgs. So that is another thing that you need to have. And from that expression, if one convert 1 atomic mass unit to energy, that will be 931 mega electron volt energy. And if we convert this to energy, then one need to divide by c square, as E is equal to mc. So the energy will be then 1 u over c, or mega electron volt over c square. So this one that we will be frequently using in this course. So with this data, and also we know that the value of c. Now using these numbers, one can find out the mass of the protons in atomic mass unit, and also the neutron mass in atomic mass unit, and also the electron mass. So using these numbers, first we will be solving example, and then we will convince ourselves that there is a trend in the binding energy, or the binding energy per nucleons for all the elements. So first we need to use that expression for the binding energy to calculate the binding energy and also the binding energy per nucleons for this element iron, and also for the uranium 238. So we'll start with the binding energy expression, and then we will be using the data. For example, with this iron, the Z number is 30, the number of protons, and mass of a single neutral hydrogen atom is this much, that one can calculate with the help of those conversion factors. The neutron number is 26, and then one need to multiply with the mass of the neutron, as I have shown you on that previous slide. Then minus mass of the iron in atomic mass unit is this much, and then if we convert this expression that is in atomic mass unit to energy directly, then one need to multiply with this factor, so that the c square will be cancelled out with this c square, and then we will be left with mega electron volt. So the energy, the binding energy for the iron is 492 mega electron volt. That is, this much energy is required to separate, or to remove, or to separate all the nucleons. All the nucleons number in this system is 56. Now to find out the binding energy per nucleon, we need to divide it by the total nucleons number. So that is 56. That is the number of proton and number of the sum of the proton and neutron. So that is around 8 mega electron volt. Now similarly, one can solve the uranium system for the binding energy. We'll be using the same expression, but in this case the Z number is 146, the N number is 92, the mass of the neutron is here, mass of this uranium is in 238 in atomic mass unit, and then as I told you, using this conversion one can find out the binding energy in terms of the mega electron volt. So the binding energy for the uranium 238 is around the 1800 mega electron volt. Again, if uh, one find out the binding energy per nucleon, that is again around 8 mega electron volt. So you see the binding energy per nucleons in these two examples comes out to be around 8, and the binding energy is different. Now if one calculate on the next slide, I will discuss the assignment for you just to calculate the binding energy for different elements of the periodic table, and so that to convince yourself that this is around the binding energy against A is around 8 mega electron volt. This is binding energy per nucleons, or we can say binding energy divided by the mass number. And this is 5, this is 10, so this is around 8 mega electron volt, with the few exceptions that we will discuss in the coming lectures. So roughly they are the same. So you need to find out the binding energy per nucleons in that assignment. But before moving to the assignment part, another important aspect that is also well tabulated and important to understand, and it is similar to the binding energy concept, that is the neutron separation energy and the proton separation energy. So first, the neutron separation energy in this course, following the Crane notation, we will be using the Sn, S for the separation, and then N for the neutron. Similarly, S for the separation and P for the proton. Is the amount of energy needed to remove a neutron from a nucleus. Say this is just a random nucleus having mass number A, the Z number, the proton number, and the neutron number is N, equal to the difference of the binding energies between these two random elements. So if we see that if we remove a neutron from this element, so that the mass number will be decreased by 1, so that it will be now A minus 1, and also the neutron number will be decreased by 1, so that, and according to this statement, the neutron separation energy is just the difference of the binding energies of these elements. Now that can be worked out to find out the mass energies, that is the mass energy of this element plus the neutron, rest mass energy minus this thing will give you the separation energy. Similarly, the proton separation energy is the same, but now if one remove a proton from this element, so that it will be now A minus 1, but instead of N minus 1, now it will be Z minus 1, because now we have removed a proton, so that the proton number will be decreased. So that will be the difference of the binding energy that one can work out in a similar way as we have discussed the binding energy. So these are the two similar things that one can calculate for any random system. And on the coming slide, we will see a trend of this new separation energies for the neutron and also for the proton separation energy. So before going into that part, it is that the proton and neutron separation energies are typically in this range, that is 5 to 10 mega electron volts. So on the previous slide, I have told you and shown over that figure that the binding energy per nucleons is around 8 MeV. So again, these separation energies are also of the same order as we have seen on the previous slide. So you need to work out on these problems just to make sure that the binding energy and the binding energy for the various elements, for example, we have very light element, we have the intermediate weight element, and we have some heavy elements. So for all the situation, the binding energy per nucleon will be just around 8 MeV. Also, these are other few systems. You need to calculate the binding energy and the binding energy per nucleons. This is the third problem on the binding energies. These three are taken from your course book. You need to just find out and just verify uh, the 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 trend that these elements are showing with respect to the binding energy per nucleons. Also, you need to calculate the separation energies, the neutron separation energy and for the proton separation energy for these elements using those expression. And you need to just make sure that those answers will be in the 5 to 10 mega electron volt regime. And this is the last problem in which you have to find the neutron separation energy only. So for the assignment point of view, your binding energy per nucleons must follow this trend, the binding energy per nucleon for having different elements, having mass number. As I told you, we have lighter element, intermediate weight, and also the heavyweight elements. And also the separation energy must follow this kind of trend. This is taken from the modern physics book by the same author, Kenneth S. Crane. That is the range over this entire neutron number. Remember, this is a neutron number, not the mass number, but one can see that these are just fluctuating. So this also gave us a hint of the nuclear shell model. That shell model we will discuss in the later part of this course, but if one can see that a slightly changed neutron number will give rise to a change in the separation energy. That is, some orbits are closed and other orbits are not completely filled. So as a result, we have these fluctuations. Similarly, one can discuss for the proton separation energy. So in the assignment problem, you need to make sure that these answers will fluctuate, but it will be around 5 to 10 mega electron volt. And with this, I thank you for your time.